Okay, find the exact area. So what do we know about areas between curves? Again, you must have graphs. So let's have a look at the graph of these two functions. So you can see there are two functions, y equals x on 2, y equals x squared minus 2x. Our points of intersection, solve them equal to each other. I haven't labelled them there, have I? So let's solve x squared minus 2x equals a half x squared minus, what's that, 5 on 2x equal to 0. So it's going to be at 5 on 2, isn't it? So 5 on 2 is one point of intersection, 0 is the other. So the straight line function is on top. So between 0 and 5 on 2 of top function, which is the linear graph, minus bottom function, which leaves me between 0 to 5 on 2 half x minus x squared plus 2x dx. So really from here, it's just making sure if it's not TeX active, we don't make any careless mistakes. So anti-differentiate, I'm going to get minus x to the 3 on 3, 5x to the 2 on 4, between 5 on 2 and 0. So I get negative 5 on 2 cubed on 3 plus 5 times 5 on 2 and on 4 minus 0. So what's that? 5 cubed is 125 on 8, negative 125 on 24 plus, that's 25 on 4 times 5 is 125 on 16. So if we make them both 48s, we get negative 250 plus 375 over 48, which is 125 on 48. We see there that our negative 125 on 48 is approximately our 2.6, which is the value we can get using our CAS if we just evaluate under calculus bounded area. But again, remembering that only gives us an approximate answer. All right, B, find the area of the region of the two graphs and the lines, blah, 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 blah. All right, so we can see from the CAS here of our two graphs, our blue function f1 of x, our red function sine 2x, and we can see that they cross over, and so the top function and bottom functions change over the interval, 1.57 being pi on 2. So we can see there that we have to split our function. So we're going to have the integral between 0 and my point of intersection, okay, a 0.5. So we can use our CAS, we could solve it algebraically. I better do that. So if I'm going to have cos 2x, cos x equal to sine 2x, which is 2 sine x cos x. Take a cos x out, bring everything to the left-hand side. I'm going to get 1 minus 2 sine x equal to 0. So that means my points of intersection are at cos x equal to 0 and also sine x equal to a half. So this one gives me the pi on 6. This one gives me 0, pi on 2 and 3 pi on 2, etc. So there's my pi on 2. The other ones would be further along. Okay, so pi on 6 is my first point of intersection, and pi on 2 there is my second one. So between 0 and pi on 6, I get top function, which is the blue. I'll use blue, which is cos x, minus red function, sine 2x dx, plus the integral from pi on 6 to pi on 2 of the reverse. Yeah, and look, and from there we've just got to be careful to not make mistakes. There's no guarantee. So equal to, let's try and split these up. So antiderivatives, so cos x is sine x, derivative plus 1 on k cos 2x evaluated between pi on 6 and 0, which is equal to sine pi on 6 plus a half cos, put pi on 6 in, I get pi on 3, minus 0 plus a half, because cos of 0 is 1. So that's a pi on 6, I get a half plus a quarter minus a half. So I get a quarter for that section. All right. Coming over here, I'll write a bit bigger. I'm going to have antiderivatives again. Antiderivative of sine is negative 1 on k cos 2x minus cos x is sine x between pi on 6 and pi on 2. So I get, let's just put things in. So pi on 2 in, 2 times pi on 2 is pi. Cos of pi is negative 1, so I get positive a half. Sine of pi on 2 is 1, minus 1, minus pi on 6, 2 times pi on 6 is pi on 3. Cos of pi on 3 is a half, so I get minus a quarter. Sine of pi on 6 is a half. Okay, looks about right. So we get negative a half minus negative 3/4. So it's 3/4 minus a half, which is equal to a quarter. For the total area is a quarter plus a quarter, which is equal to a half, which from our CAS, that's the little answer that gets generated if you do your integral. All right. Let's continue on. You can see obviously the printouts here from that previous example, where we can find our points of intersection when the equation's equal. Don't forget when you're doing trig functions, try to put a domain restriction. And we get our half, and there's the answer that we're looking for in this one. So find the region, always sketch a graph, log function. Hopefully we're pretty comfortable with our log function. That's one. And there's 2. So let's think about, so we want that area there. So that's 1, that's 2, that's natural log of 2. All right, so again, what are we looking at? We've got the integral between 1 and 2, haven't we? 1 and 2 of natural log of x dx. Now, we don't know the antiderivative of log. Again, I know the antiderivative of 1 on x, which is log, but not the antiderivative of log. So again, let's go into rectangle mode and try to work out this area about the y-axis. So what are these values? That value there is 0. That y value there is natural log of 2. So if y equals natural log of x, well then x equals e to the y. So the black area that I'm interested in now, therefore, so we go here, the black area is equal to the integral between 0 and natural log of 2 e to the y dy. Everything in terms of the y variable, which means I get e to the y evaluated between natural log of 2 and 0 is e to the natural log 2 minus e to the 0, when e to the natural log of 2 is just 2 minus 1, which is 1. So that black section there is 1. So the area of that rectangle, it's bad writing, area of rectangle, length times width, which equals 2 times natural log of 2. So that's the area of the whole thing. So that means the area of the red section is simply equal to the total area, which is 2 natural log of 2, subtract the area of the black, which is 1, which is what our CAS has given us. And the easiest mistake to make is to just, I don't know, just be careless and go the antiderivative of log x is 1 on x and substitute some values in. It's really easy to do because that's what you're thinking you need to do. So just have that formula sheet there just so you don't make one of those basic mistakes. Okay.